So today we are going to be doing Cauchy Integral Questions, Revision and Practice Part 1. Okay, now by the end of this video, which hopefully will be about 10 minutes long, I am confident that most people who've watched this video will be able to do this integral without a great deal of difficulty, and we're going to do it as example 3. But first of all, what we're going to do is we're going to go through 5 questions which will decide precisely how we answer the different types of Cauchy integral questions. Okay, so we'll come back to this one at the end of the video. Right, question number 1. Here's question number 1. Is there a pole slash singularity? And a pole or a singularity is basically some point where the function is not defined. For example, if we had, I don't know, f of z over z minus 2, well, it's not defined at 2, and therefore 2 is a pole slash singularity. Okay, now, if the answer to this question is no, there is no pole or singularity, then if f of z is analytic on the region, then by the Cauchy integral theorem, the integral around the curve of f of z dz equals 0. So you have to be careful when you're looking at these Cauchy integrals. Sometimes they are literally so easy that all you need to do is just recognise that there is no pole and that f of z is analytic, and then it's bound to be 0. So sometimes they're very easy. So just give a couple of examples. I don't know, the integral around a curve of sine z times e to the z dz, if that was on an exam paper where c, for example, is the unit circle around the origin, the answer to that, we can say without doing any calculations whatsoever, is 0, because we know that this here is analytic over the region and there are no poles. So nice and easy. Couldn't get easier than that. So just give another example. For example, the integral, I don't know, of z squared add 3z sine z dz around the unit circle. Again, without doing any calculations whatsoever, because this is analytic, there's no poles or singularities. By the Cauchy integral theorem, we know it is 0. And by the way, that answer there, just before we get on to question 2, it doesn't matter what the curve is. The curve could be a nice picture of a smiley face like that, as long as it's a simple closed curve. It could be a circle, it could be a rectangle, it could be whatever, a Mr. whatever, it doesn't matter what it is. Whatever the curve is, as long as it's closed, as long as it's simple, and as long as our function is analytic within the region, then by Cauchy's integral theorem, the integral is 0. Easy. Right, okay, now question 2, and this is where it starts to get a little bit more complicated. Question 2, if there is a pole or singularity, is it within the region bounded by C? Okay, now this is important, because if there is a pole or singularity, but it's not within the region, then question 2 types are just as easy as question 1. So let's, for example, look at I don't know, the integral of f of z over z minus 2, for example, dz. Let's have a look at this integral around the curve C. Now, we know there is a pole, there is a singularity at z equals 2, because the bottom is equal to 0 then, and therefore there's not a definite value, it's not defined. So we know there is a pole at z equals 2. That doesn't necessarily mean that we're going to have to use Cauchy's integral formula, because if z equals 2 is outside of the region bound by C, then we can still use Cauchy's integral theorem. So, for example, let's just draw our point here, z equals 2. Let's imagine that that C is this rectangle here. Well, z equals 2 is not inside that, and so therefore the integral of this, even though there is a pole singularity, because the point z equals 2 is not in that region, it's not bound by the curve C, the answer to that by Cauchy's integral theorem is 0. What about if we had a nice smiley face over here, or whatever? It doesn't matter. Z equals 2 is not in there. Only if the pole or singularity is within the region. So, for example, if C was this, or if C was this, or if C was this, or whatever, then Z equals 2 is within the region, and therefore we can't use Cauchy's integral theorem. We have to go on to question 3. Okay, but it's really important. Just because you see a pole, it does not mean that you have to go onto Cauchy's integral formula. We could still use Cauchy's integral theorem if the pole is not in the region about which we are integrating. Okay, so that's question number 2. So you would ask each of these questions yourself when you see the question in an exam. Okay, let's have a look at question number 3. Now this is actually what the topic of this part of the video is about. Question number 3, assuming that we do have a pole or singularity and it is within the region bounded by C, the question you have to ask yourself next is A, is there only one pole? And B, is the pole of order 1? And the order of a pole is, for example, z minus a, I don't know, let's say we had f of x over z minus a cubed, well that is order 3. If it's z minus a squared, it's order 2. If it's just z minus a, it's order 1. And if there are more than one pole, for example, you could have f of x over z minus 2, z minus 4. Well, in this case, there are 2 poles at 2 and at 4. So question 3, which is the question type we're going to be dealing with today in part 1 of this 3-part video series, is when there is a pole, it is within the region, there's only one pole, and it's a pole of order 1, which actually is the most common type of question. Okay, now question 4, which we'll do in the next video, so I'll just give you a quick preview. That is, how do we proceed if the pole singularity is of order greater than 1, i.e. if it's f of x over z minus 3 squared or whatever. We'll do that in the next video. And then question number 5 here is, how do we proceed if there are multiple poles, i.e. if we're on this one here, what do we do then? We'll do that in the 3rd video. Okay, but in this video we're going to focus on the most common question type, where we can't use Cauchy's integral theorem because there's a pole which is within the region bounded by C, but there's only one pole and it's a pole of order 1. Okay, so we're going to do 3 example questions, so let's get going. Okay, so example question number 1 is this little beauty here. Okay, so we have a singularity slash pole at z equals 2. And the first thing we need to do is we need to check, hang on a sec, is z equals 2 within the region about which we are integrating? And if it is, we have to use Cauchy's integral formula. And Cauchy's integral formula, just as a reminder, we have done this in a previous video, but Cauchy's integral formula is f of a equals 1 over 2 pi I, the integral around c, f of z over z minus a dz. That's Cauchy's integral formula, and we use this when a is within the region about which we are integrating. So we're going to use this in this question. But first of all, what we need to do is we need to have a look at the region, and we need to just check, hang on a sec, is the region include the point z equals 2? Well, let's have a look. So C is a unit circle centered at z equals 2. Okay, now I'm going to try and draw the region here. So it's centered at z equals 2. Here is the point z equals 2. And here is a unit circle. Oh, let's hope that this goes right. Oh, that's not bad. Good. Okay, there's the unit circle. So this here is C. Z equals 2 is the centre. It's the unit circle, i.e. it's got radius of 1. Not that that matters. All that matters is that Z equals 2 is inside that circle. And therefore, we cannot use Cauchy's integral theorem. We have to use Cauchy's integral formula. And the other thing that we need to know is whether it's counterclockwise or clockwise around the curve. In actual fact, this is relatively easy. All you need to remember is if it's counterclockwise, then we use this formula here. If it's clockwise, then basically we can use this formula here and then just put a minus in front of the answer. So if it's counterclockwise, it's this one. Clockwise, put a minus in front of the answer. Now this looks a bit horrific, but in actual fact it's not. So what we need to do, let's have a look. We need to get our integral here in the form f of z over z minus a. Well, clearly f of z is going to be this and z minus a is going to be this. So we have to let f of z equal e to the z, and we have to let a equal 2. So we know what we can do now, because we know that it's holomorphic, it's analytic within the region. That goes without saying. E to the power of z is analytic all over the place, so it's certainly analytic within this region here. Okay, so we have f of z is e to the z, and we have a equals 2. Now here's the easy bit. Okay, all we need to do, because we know that the pole is within the region, all we need to do is just fill this in. So f of we're using the formula f of a equals 1 over 2 pi I, the integral around c, f of z, z minus a dz, which actually I've already just written. Okay, so put a equals 2, we have f of 2 equals 1 over 2 pi I. The integral around the c, f of z is e to the z over z minus 2 dz. And here we have the integral that we are trying to find here. So basically the answer is f of 2 times 2 pi I. Well, f of 2, if f of z is e to the z, then f of 2 is equal to e squared. So the answer is 2 pi I e squared. And that is it. Now, had it been clockwise instead of counterclockwise, we could have done it exactly the same, but in the end, we would just plonk a minus in front of it. And that's it. These questions are not that difficult as long as you're comfortable with knowing where the poles are and the singularities and everything like that. So let's have a look at another question. Okay, let's go on to the next one. Example 2. Okay. So again, we're going counterclockwise around the curve C. The curve C is described thus, and here is our integral that we have to do. Okay, now, to be honest, the most complicated thing about this is understanding what this means, but all this means is that Z, the curve C, is I plus this bit. Now, e to the I theta is basically a unit circle around the origin. That is e to the I theta, where theta goes from 0 all the way around to 2 pi. So that's e to the I theta. So 2e to the I theta is basically just a circle centered at the origin with a radius of 2. And I plus basically just means that it's been translated up where the center is now I. So basically, if we draw our region, we have, here's the point I on the 2i, isn't it? Sorry, here's the point 2i. Oh, my apologies. Right, so the circle is centered at the point I. So here is the point I. Okay, and the radius of the circle is 2. So that will basically bring us, and again, let's hope that I managed to do this correctly. That's a pretty awful circle. Hopefully, yeah, sorted itself out. Good, excellent. So here's I, the center, and as the radius is 2, that means that this point here is minus I, and that means that this point here is 3i. And most importantly, this is the curve. We want to know, well, the pole is z equals 2i. That's the pole, that's the singularity. Is 2i within this region? Well, 2i is here, and the answer is yes, 2i is within the region around which we are integrating. Therefore, we use Cauchy's integral formula. We can't use Cauchy's integral theorem. And Cauchy's integral formula, just a reminder, f of a equals 1 over 2 pi I, the integral around c, f of z over z minus a dz. Okay, so clearly here what we need to do, let's just compare this and this. Well, clearly f of z is going to have to be z squared, and a is going to be 2i. So we let f of z equal z squared, and we let a equal 2i. And literally all we need to do now is just plug it all in. These are easy questions once you get your head around them. So that's f of 2i equals 1 over 2 pi I, the integral of f, or z squared, because f of z is z squared, over z minus 2i dz. And this bit here is the integral that we seek here. And therefore, the answer is f of 2i times 2 pi I. And f of 2i, well, f of z is z squared, so that equals 2i squared times 2 pi I, and 2i squared is minus 4, so that equals minus 8 pi I, and that is the answer to the second one. And by the way, if it had been clockwise instead of counterclockwise, then all we got to do is just flip that sign at the end, and it would have been plus 8 pi I. Okay, now let's get on to the third one, which is the one that I said at the beginning of this video. I claimed that you would be very confident in answering by the time we got to the end of this video. Well, let's see how confident you are. But I think that we're all going to be able to do this quite easily. So let's first of all have a look. Is there a pole? Yes, there is. The pole is at z equals minus pi over 2. Is this analytic? E to the z sine z? Yes, it is. Okay, so that's our case. So now what we need to do is we need to have a look at the region and see if the pole is inside the region, because if it is, then we can't use Cauchy's integral theorem. We have to use the formula. So let's have a look. So C is the rectangle. Okay, so let's draw our C here. So C is the rectangle with coordinates at the corner. 0 minus 2 pi, that's here. 0, 2 pi, minus 2 pi, and minus pi, 2 pi. So basically C is this rectangle here, and we're going clockwise here. Again, all we need to do is do exactly the same as if we were doing counterclockwise, and then remember just to flip the sign at the end, but we are actually going to go clockwise around it. So all we need to do now is see, hang on a sec, is the pole within the region about which we are integrating? Well, this is the point 0, this is the point minus pi, and the pole here is at z equals minus pi over 2. Yes, it is inside the region, therefore we need to use Cauchy's integral formula, which we have already stated is f of a equals 1 over 2 pi I, the integral of f of z over z minus a dz around the curve C. Okay, so clearly what we want to do here is we want to make f of z be e to the z sine z. So we let f of z equal e to the z sine z, and we let a equal minus pi over 2, and then all we got to do is just stick those values in so that we get f of minus pi over 2 equals 1 over 2 pi I. Actually, I've run out of space here, so let's just write it again. F of minus pi over 2 equals 1 over 2 pi I, the integral of f of x, which is e to the z sine z over z minus a, and a is minus pi over 2, so that's z plus pi over 2, dz, which is exactly what we are looking for, and therefore the answer, what we seek, is f of minus pi over 2 times 2 pi I. F of minus pi over 2 is e to the minus pi over 2 times sine of minus pi over 2, just from there, and that equals sine of minus pi over 2 is minus 1, so that equals minus e to the minus pi over 2, and therefore our integral is equal to minus e to the minus pi over 2 times 2 pi I, but remember that's clockwise. They want, sorry, that's counterclockwise. They want clockwise, therefore all we need to do is get rid of the minus, and therefore the answer to this is 2 pi I e to the minus pi over 2. And that is that. So basically we've done 3 examples here where there is a single pole, and the pole is of order 1, and the pole is within the region, and we've had to use Cauchy's integral formula, which once you get used to it is pretty simple. And if you do see these questions in your exam, hopefully you should be able to get full marks on them now. Now in the next video we are going to be looking at question 4, which is basically slightly different if the pole or singularity is greater than 1, and then in the third video we're going to do what happens if there's multiple poles or singularities, i.e. like this one. Okay, well I hope you found this useful. I hope you get these questions on your exam. If you do, then please like this video and subscribe to the Gresty Academy YouTube channel. Thank you.